switch from slides to switch to my desktop. So this is, I am now logged. This is a directory on a cluster that has, I believe right now it has 192 cores on 24 compute nodes with 8 cores. It has dual processors with 4, so it's a dual quad-core compute nodes, so 24 compute nodes, and 24 compute nodes, dual quad cores on each compute node, and so 8 times 24 is 192, I believe. That's, let me go back just. Lucia, I'll answer your question as I start running this job. So this is a dynamic rupture benchmark. This is a 2D benchmark that is a spontaneous rupture, but that's really the details of the benchmark don't really matter. But the way I run this in serial is I do try3.cfg, and then there's a resolution. I'm going to do the coarsest resolution to make things run faster. There's a gradient in the discretization size versus the uniform discretization size. And so those are my general, if I'm running on a desktop, I'm going to do something like that. However, I'm running on a cluster, and I created a special file for this PBS system. And so I add that to the command line. And so this is what that file looks like. So this is that file that I had, very similar to what I had in that last slide. And you'll notice that I have it in .pyr pilotapp, and in this case I have pilotapp_pbs.cfg. If I were to name this file pilotapp.cfg, Pilot would actually read it automatically from this directory. There's a couple different cases that I use on my cluster here. So I have a number of pilot app files. So I have things for, like, if I want to do a test case on the front end, I'm doing this configuration. There's also other configuration files for if I need to run the SunGrid engine. Here was my configuration file for Lone Star. And so what I tend to do is when I'm running on the cluster, I tend to actually just always put these on the command line. But you could put them in a pilotapp.cfg file in your .pyr pilotapp directory, and they would be read automatically. So let's see what the first line of my .cfg file is a hint to myself that you need to give these other command line arguments that are job specific. And then here's my sort of basic parameters that tells it to use the PBS batch system. Use your bash shell. Always send me email. Send me email at the beginning, end, or when the job aborts. Copy my environment variables, and then here's my launch command. And so here's what I showed on the slide. I'm using OpenMPI, and so that allowed me to add these 3 command line arguments. I'm going to bind to core, so I want processor and a memory, what's called processor and memory affinity. That means when you're setting up the job and launching the job, make sure that the memory you're using for a particular core is as close to that core as possible in the hardware. Then also assign by socket. So that's the order of whether I use all of the cores in one processor before I use any cores in the other processor that's there, or do I use 1 core from each processor, then 2 cores from each processor, 3 cores, or 4 cores. And then I tell it to report the binding, so tell me which processors and cores you used on each socket. And then these are some sort of optimization communication parameters related to InfiniBand that I have set up and using that I'm basically using in all of my jobs. Most of these come directly from what was the defaults on Lone Star, and so basically I tend to use those. There's this one that is often needed on InfiniBand systems because of how PyList starts. But generally these others you probably don't need, but you may want to look at your, if you're running a computing center, look at what they recommend in terms of the MPI parameters for their versions of MPI that they have installed. And so here I am in my directory. I need to run in parallel. I need to do pilot try3.cfg. I'm about to run out of battery. Try3.cfg. Then I want to do try3_2 gradient.cfg. Then I want my pilot app underscore PBS. And so let's see what's going to happen. So I'm going to do scheduler.try to see what bash script is going to be sent to the batch system. So if I scroll up, this is what it did. It just did a dry run. So it created this bash script that starts off as every other bash script. Then these are PBS-specific commands. So that's what this comment character PBS is saying. This is telling a PBS batch system to grab these variables. So this is the shell you're going to use on the compute node. You'll notice I forgot to give it my job name, so it just is going to call it job name, which is the default. Send the output to standard out. Send your error to standard error. I didn't give it the number of nodes, so it's going to use one node. I did not give it the processors per node, processes per node, so it's going to use one. Then it's going to do my those qsubmit commands that I included. It's going to then switch to the working directory. So Pilot knew that you're using a PBS system. This is the type of script that I need. And then it's going to start the job by running nemesis pyr start. And so this is going to start Pilot up. It's going to do the validation. And then when it does start on the compute node, that's what this comment down here is. This is saying, when I launch in the compute node, this is how I'm going to do it. And so it's going to call MPI run. So it's going to notice that up here, we did not launch in parallel. So this initial validation is done by the bash script before it's actually submitted to the job, but it's done in serial. Then when it starts up on the compute node, it's going to run in parallel, and it's using my MPI settings that I set here. Then it's adding in the Python path, and then it's adding in the other commands that I had. So, and then it says when I submit it to the queue system, this is the command I'm running. I'm running the qsubmit command, and basically I'm running the above script. So I need to go back and pick up. So I'm going to copy these parameters that are my reminder. So I'm going to do -- nodes equals, let's do 8. So I'm going to do 8 total processes per node. Let's do 4. So we'll end up using 2 compute nodes, each with 4 processes. We have 8 cores per each, so we'll sort of load up half the compute node job name. Let's just call it ptest. Let's write it out to ptest.log. And I think I still have my my scheduler.dry. So let's look at the difference. The difference is now notice here nodes equals 2. So Pilot took my -- nodes equals 8 and said, well, actually what the PBS command is you give it nodes equals 2, where that's the number of compute nodes, and then on each compute node start out 4 processes for a total of 8. So it did the math necessary and knew that this batch queue system did things in that particular format to specify on how many nodes to run. And so this is going to start up. If I look at my key system here, you'll see that here's my p-test. It's running. If I load up my web browser, here's the cluster, and someone's currently running on the other half. The job is starting up. I can look at my job queue. There it is. I'm running. Let's see. So it's still, there's a little bit of delay before it actually will start up. Showing up, I can look at my cluster top. And so this is showing everything that's running on the machine. Let's see just what I am running. So there's the job. You can see this. Let's see. Let's go to the scroll to the top. So here's the amount of memory here's the percentage memory being used and the percentage of CPU. And so if we scroll down, notice that at this point it's just starting up, so I'm only getting, a fraction of the total CPU. Here's how much memory I'm using, so I'm not using that much memory. As we update here, you can see I'm starting to use more CPU. Still not using very much memory. This is a pretty small job, so that's why. And you'll notice here you can see I'm running on compute node 10 and compute node 11, 4 processes each. So now you can see my CPU usage has gone up. So we're starting to actually run. If I go back and sort of see what my system is looking like, it still looks, so it doesn't look like it's updated my system job queue. So runtime, it's running. So I said it was running on compute node 10. So I'm going to go here and I'm going to run. I'm going to go to compute node 10. And I know that the log files are actually sitting in, because it's a torque malloy scheduler, they're running in torque spool. I look here, and I don't see my job, so is it still running? It is. So maybe it started up on 11. So here I am. Here's my current error file. Here's my current output. I can sort of see where we are in that output file. So it's basically the process name of the computer and then OU. So it is, here I can see that I've computed 7 seconds of the simulation. It's going to go up to 12, so it's a little over halfway through. You can see my time step here was advancing from 0.48 to 7.5, so it's a time step of 0.02 over 12 seconds. So it's doing several thousand time steps. If I look at the top of that file, you'll notice that here's the usual initialization. So it initialized. After it finished adjusting the topology, when I'm running in parallel, it distributed the mesh. And so it's telling me that that's when it was distributing it. As part of that distribution, it partitioned the mesh, and then it distributed the mesh across all of the processors. And then once it's distributed, then it can start doing the pre-initialization and really run. That's when it really starts kicking in and running in parallel. So relatively straightforward in terms of, let's see. So the job is done. And so let's look at here where I am. So it is copied. I didn't give it a name for my error file. So let's look and see what is in my error file. So my error file contains that when I told it to report the binding, it's telling me that what it did is by doing the by socket, it used socket 0, and it was using core 0001. Then it used socket 1, core 0010. Then it used the third process it started on was core 002, and then it used socket 1, and that's identified by core 0020. So this is telling me exactly what cores it was running on the first compute node 11. Notice I don't have that information for compute node 10, but it'll be the same. Then I have some warnings here in the output file about no initial state given from my friction model slip weakening using the default value of 0. That's fine. That was what I wanted it to use. Now let's if we look at the end of the ptest.log file. So we're going to here's all the events within each of those stages. So let's get up to the top of the PETSI log summary. So here you can see it was the main or root node was compute node 11, and it was used a total of 8 processes. It told me, I'm using the PETSI development, so it actually tells me exactly which version of PETSI I was using. It took a total of 204 seconds. Tells me the total number of flops. Here's my stages. In this particular case, this is a pretty small problem. It spent, before I think that large 3D run was like 50%, 56% in reform residual. This is only 36. Now my output, because it's a smaller problem, it actually ended up taking up 12% of the time. And for each of those stages, I can see exactly where it spent time. So if I scroll down here to the reform residual, you'll notice that so this is my absorbing boundary reform residual. Then this is my faults integrate residual. You notice that it's sort of hard because these values run into each other. But all of these are using 10 to the minus 2 to 3. And then my elasticity integrate residual, the compute phase, used 1.8 seconds of compute time. So what this means is that the setup of my integrate residual took, a few 10 to the minus 3. My integrate residual for the elasticity took 1.8. So basically, I can get all of the absorbing boundary conditions and fault information for free compared to integrating the elasticity term in computing the residual. So this really gives you an idea of where you're optimizing a specific routine is important. Spending time optimizing my faults in terms of runtime and getting really high flop rate is not going to do much at all to decrease my runtime. Notice here our flop rate. This routine is pretty efficient, so we're getting 1 gigaflop per second. And so here's you'll see most of it. Here's time adjusting my solution space, so that's a particular part of the solver routine. Takes up most of the time compared to the actual solving itself. So this is actually doing all of the fault-related stuff. The fault constituent stuff is included in that step. Any questions on running in parallel, running on a cluster, trying to set up submitting to a queue? So I think I did have one more slide, so let's go back. So that final slide, this was just to give you information that I want to point out again that in order to debug if something goes wrong, you can use even on a cluster, you can use the help properties and help components. We'll go back to the cluster and I'll run this pilot info and I'll show you where the cluster information is also showing up there, because that pilot info command dumps all of the pilot information parameters, not including everything about running on the cluster, all of our batch specific commands that we specified. Then here's reminders of you can use the scheduler-help, and so we'll go back to the cluster and run that, and scheduler dry to do dump the script that's used for the batch submission to stand it out, and that's for the dry run, and that's launching. Also, you can do it for the launcher for how it's launching the compute nodes. Generally, you don't need to. You won't be using the launcher dry, but you will definitely be using the scheduler launch dry to make sure you're launching properly in the way you think you are on the batch system. So we're going to do the pilot info and the scheduler help. So let's share the desktop. So instead of back here we're submitting, we're going to go scheduler help. And so this tells me what properties I can get help in and to use to get more information to help that property. So I'm going to do scheduler.help properties. You didn't notice it didn't tell me anything really about any components that I had. So here's one of the options here is the actual command to submit to the queuing system. So for when I set it for the PBS, the default is qsubmit, qsub, sorry. And so if your particular version of PBS use some different command or is alias to something else, you could change that. And so I could do something like --scheduler.command equals, I don't know, qsubmit. If it was called qsubmit22, it would be qsubmit22 or whatever like that. You could do it on the command line, or you could add that into your special pilot command file. So here, here's the dry. It's a Boolean value. The default is false. It's currently false. The help components, help persistent, those are just the help. Here's my processes per node. Default value is 1. My current value is 4. Notice it tells me it was set from the command line. My qsubmit options, this is just a list. Notice that, this is what it looks like, and it tells me where I got it from my pilot underscore pbs.cfg file, and it tells me the line number where it picked that up. There's a resource list. So this is specific to the PBS if you want to limit the number of resources in a particular job. So you can say, well, if the job's still running after 5 hours, I just want it to stop because I think this job should run in a couple hours. The shell to use, notice that the default is just a normal simple shell, and I've switched to bash shell. Wait for the job to finish. I'm not sure particularly what this option is for, but it is, I don't make any use of it. But you could look it up probably in your PBS system about whether it supports a wait command or not. I guess one final thing, are there any questions that have come up in your mind about running? And so let's see, the other thing I was going to do was the pilot info. So I can delete that, go back here and run pilot info, I'll do verbose. It's going to dump. So the pilot info doesn't know about the -- node. So it does not know about the running in parallel. So here's one issue with the pilot info that I failed to mention is that it does not allow command line arguments because it has its own command line argument -- verbose, and so I have to remove these additional command line arguments that I was sending directly to pilot. So when I dump out my parameters, it's not going to have those parameters these parameters here that I added on the command line. But it will have my PBS parameters. So let's see what my pilot parameters file has in it. And so notice before I sort of ignored this fact that I had this -nodes. And so all along, this information about running on multiple processes is sitting in our nodes. Also about the job information in the scheduler. So scrolling down, there's the launcher information that we sort of ignored before, and the default is to launch using mpitch. So here's that the information. It's still using even though I'm using OpenMPI jobs start the same way that mpitch jobs start. So I don't need to change the default launcher from the mpitch launcher. And here's all of my PBS commands that were coming from about how to launch the job that I set in my PBS file. Here's the machine file. The default is mpirun.nodes, but obviously that PBS knows how to change that to something more specific. If you have a cluster where your nodes are named a specific way and you want to set that, and you're not using a queue system, but you need to create a file with the names of the nodes that are generated a certain way, you can actually generate them. Pilot will generate that node file. You give it the pattern and the node list in terms of the number of processes to fill in that node list, and it'll generate this machine file for you. And this is covered a bit more in the manual. This is now relatively rare these days because almost everyone is using a batch system. And so now we're getting back into our other pilot parameters such as the mesh generator. And so that one thing that doesn't run in parallel, there's the distributor, there's a partitioner, and I set my partitioner up to be Parmenas. When I ran on just my local laptop, I used the Choco partitioner. I believe in the binary we only include the Choco partitioner. But I've set things up on the cluster to use Parmenas or Choco. I tend to prefer the Parmenas partitioner, and that partitions the mesh across the processors. Write partition I've set to true. That was set up in my pilot.app.cfg file. The data writer for the partition I've set to HDF5 mesh. And it is actually an HDF5 external mesh data writer, so for maximum parallel performance. And the file name is going to write to partition.h5. All the rest parameters are specific to my simulation. We haven't seen any questions. We have about 25 minutes left of this schedule B last session of the tutorial. This is your chance to ask questions about running in Pilot a little more interactively than through email to the CIG shortlist. So are there any questions?